Okay. Uh, yeah. Apologies for the slight delay. Just had some issues setting up the things, but yeah. Let's start with today's session. So, can someone confirm whether I'm audible and whether the screen is visible or not? Hi, Hari, Hari. Um, okay. Okay. Fine. Let us just get on with today's session. So, welcome again to another session for live sessions of technologies for clean and renewable energy production, an NPTEL course offered by Professor Mandal from IIT Roorkee. And yeah, let's get on with it. So, for the last couple of weeks, we were looking into things like coal, basically, and uses of coal, and then we started looking into petroleum, or how crude oil is produced, how it is refined, and what are the different fractions of crude oil from refineries and so on. So today we'll be looking a bit more into crude oil. Mainly, we want to uh, learn about the impurities that are present in the crude oil and how do we remove these impurities, and what is the need for removal of these impurities and so on. And there are mainly a couple of impurities, mainly sulfur, nitrogen, and metal. So we'll see how these impurities are removed. you know some processes are called sweetening processes, and some processes we call them hydroprocessing or hydro treating. So we'll just briefly look into this. So yeah, just before I move on again, just reiterating the fact that I will just be running through the lectures that Professor Mandal had taken for the week 4. I am expecting all of you guys, learn from those NPTEL lectures regularly, and this session is only meant as a supplement for those lectures taken by Professor Mandal. So yeah. So, anyways, getting on with today's session. So, the various kinds of impurities that are present in petroleum or crude oil are, sulfur, nitrogen, oxygen, and metals, and also includes inorganic salts and water-soluble salts. That are present in the crude oil when we drill them out from the earth's surface or from under the sea. So we need to improve. We need to remove these impurities, mainly to achieve the quality of the finished products. So, for example, if the crude oil or the petrol or diesel that we refine from the crude oil has very high nitrogen, usually it will give us a reddish brown color if it has a high nitrogen. And odor, presence of sulfur and nitrogen compounds can emit very foul odors. D. Yeah. So foul odors and pungent odors. And the stability, high presence of oxygen can reduce the stability of the oil and so on. So we want to improve the quality of the fuels that we produce from crude oil, and for that we need to remove these impurities, which are mainly sulfur, nitrogen, oxygen, dissolved metals, and salts. So removal of sulfur compounds is generally called as sweetening. So crude oil that has a very low sulfur is generally called as sweet crude. And usually, when we compare it with general crude oil prices, sweet crude are usually slightly more expensive compared to sour crude. which has high sulfur content. So removal of sulfur are usually conducted in two main ways, mainly by alkali extraction and hydrotreatment. So these are the some of the sulfur and nitrogen compounds that are usually detected in crude oils from all around the world. It could be straight chain sulfur compounds or nitrogen compounds, or it could be aromatic like this pyrrole, indole, carbazole, and so on. And it could also be polyaromatic. For example, this dibenzothiophene or naphthenobenzothiophene, or something like a benzoquinone, like and so on. So these are just some of the nitrogen and sulfur compounds that are present in the crude oil. So we'll just briefly look into the different kinds of sweetening process or mainly removal of sulfur. So the first process is caustic wash. So caustic wash basically means we just wash our crude oil or the oil with sodium hydroxide, and we use this sodium hydroxide to remove the sulfur based compounds. So yeah, so caustic wash we use a mixture of water or water and sodium hydroxide. So basically a solution of sodium hydroxide, or also known as caustic soda, and we mix this with the petroleum fraction. And the major reaction that happens here is this. So RSH, so as we saw here, RSH is a type of sulfur compound that is present that we can detect in crude oil. So this sulfur compound reacts with nitrogen, not nitrogen, sodium hydroxide to form NaSr, or sodium sulfide based compound, and water. And based on this reaction, we can remove the sulfur compound from the crude oil. Then the next treatment would be doctor treatment, where basically we would use sodium plumbate solution. So in the caustic treatment, we were using NaOH, and here we'll be using Na2PbO2, which is sodium plumbate solution, and elemental sulfur to remove the mercaptans in the form of disulfides. So these are just some of the reactions that are present during the doctor treatment. So the mercaptan will react with the sodium plumbate to form a lead-based sulfur complex PbSr2 and sodium hydroxide, and this PbSr2 will react with elemental sulfur to form sodium disulfide compounds RS2R, which is this one basically. So like that the reaction proceeds, and finally we'll get the final compound as lead oxide and sodium disulfide, along with some amounts of sodium sulfide and so on. But yeah, this is the slight difference between the previous caustic treatment and this doctor treatment. Basically a different chemical solution that we are using. Then we have copper sweetening, where basically we'll be using a copper chloride to convert the mercaptans or RSH products into disulfide, basically having S2. So here also you have a variety of these different steps in the reactions, and some of the disadvantages of this process is that some oil soluble cuprous mercaptide remains in the treated oil. So this is basically CuSr. This can get trapped with oil. So that means some amount of sulfur is still remaining in the oil, and that is one of the biggest disadvantage of this copper sweetening process. And copper chloride can also react with naphthenic acids, phenols, and other polar compounds to form oil-soluble copper compounds. So again, the some amount of impurities can still remain, impurities in the, from copper basically. So copper based complex are metal impurities. So these metal impurities can still remain in the oil phase, and is pretty difficult to get it separated. And then oil soluble cuprous mercaptide oxidation to copper oxide, causing failure to pass water tolerance test. Again, basically all these disadvantages are based on the impurities of copper, along with some addition to it, mostly copper based mercaptans or so on. So most of the disadvantages here are metal based impurity disadvantages. And then the final treatment, which is one of the widely followed treatment, is the Merox process. So Merox process is one of the most successful treating processes licensed by UOP in 1958, and this completely replaced the older process like the caustic wash, doctor treatment, and so on. So just see how this mercaptan Merox process basically reacts with. So there is a reduction reaction first. So the RSH or the mercaptan first reacts with sodium hydroxide to form sodium mercaptide and water. And then this sodium mercaptide is oxidized. So the second step is oxidation. Is oxidized in the presence of oxygen and water to form sodium hydroxide and sodium disulfide. Right. So I'll just show you the flow chart of this Merox process so you can understand the process better. So you have the feed oil here. So it goes through a caustic pre-wash where this is washed with NaOH. The oil is washed with NaOH, and this reaction occurs here. The NaOH plus RSH giving sodium mercaptide and water. So all the mercaptan containing compounds will form this sodium mercaptide and settle at the bottom. And all the oil that are that doesn't contain this sodium, this doesn't contain the sulfur compounds, will settle at the top, and this can be separated through a variety of settlers and filters to get the treated product, which is basically sulfur free. And the sulfur rich compound, which is usually in the form of NaSr or sodium mercaptide, you will usually settle at the bottom of the extractor, and from there what we can do is we can send it to an oxidizer where we pass air as well as water in the form of low pressure steam to oxidize the sulfur rich settling product or the sodium mercaptide, as the second reaction shows here. So this second reaction happens here in the oxidation chamber, and finally you will get the disulfide oil. So this is just a brief overview of the Merox process that are used for separating sulfur compounds from crude oil. And some of the applications of Merox processes are as given here. So you can see you can use Merox process for almost all the crude oil fraction, varying from LPG and all the way up to straight naphtha, gasoline, and kerosene, turbine fuel, aviation fuel, and so on. So removal of sulfur is actually essential. For one of the main reasons is that if sulfur is present in your oil, when we use it in our bikes and cars and everything, these usually form sulfur oxide emissions. Something like SO2, SO3, and so on. And these are actually harmful for the environment, and that is one of the main reasons in terms of the sustainable aspect of environment, why we need to remove the sulfur and sulfur related compounds from crude oil. And the same goes for N also, the nitrogen also. So if nitrogen is present in your crude oil, usually this will lead to NOx emissions, NO2, NO3, and so on. These are also pretty harmful for the environment, and that is why removing both sulfur as well as nitrogen from crude oil is an essential part of the current day refinery process. And after sweetening, we have one more process, basically hydro treating or hydro processing. So, very simple terms, what we do in this hydro treating or hydro processing is that we just add hydrogen to the oil at high temperatures and pressures to remove the sulfur and nitrogen compounds. So, hydro processing basically is the thermal conversion of the process in which hydrogen is used to accomplish the objectives of the refiner, which is basically to remove the sulfur based compounds. And then you have hydrotreating, which is also again using hydrogen to convert heteroatom constituents to their heteroatom hydrogen analogues and hydrocarbons. So, for example, if we had sulfur in the crude oil as RS R1, basically R is the alkyl part, CnHm. So, sulfur is attached to a hydrocarbon part, and we add hydrogen to it at high temperatures and pressure. What happens is this sulfur will form hydrogen sulfide and gets removed from the oil part. And this hydrogen then goes on and substitutes the part where sulfur was present in the hydrocarbon. So now we get a clean fuel along with hydrogen sulfide. And this hydrogen sulfide can be separated and scrubbed out from the oil. So in this way, hydrotreating, we can improve the quality of the oil by removing the sulfur in the form of hydrogen sulfur. And then we have hydrocracking, so which is also basically an extensive thermal decomposition process using hydrogen to remove the heteroatoms like sulfur and nitrogen, as well as to crack heavier molecular weight compounds. So let's say we had something like C40H82, something like that, which is a very heavy carbon fraction. We can crack this into something like C20, H32, or not 32, it's 42, yeah, or C10, C15, like that. So we can crack these heavy compounds and we can bring down their carbon value, so we can use them as fuels. So that is also possible through hydrocracking. But the biggest difference between hydrotreating and hydrocracking is that the coke formation, or basically carbon residue formation, is mitigated or avoided in the case of hydrocracking. And when it comes to the operating condition, the major differences between hydrotreating and hydrocracking is the residence time or the time at which the reaction temperature is maintained, and the extent of decomposition of the non-heteroatom constituents and products, basically. Okay. So yeah, so these are just some of the reactions that we can observe in the refinery process, mainly in the processes of hydro desulfurization and hydro denitrogenation. So basically, what we do in all these steps is that we add hydrogen to our oil to remove the sulfur based or the nitrogen based compounds, through a variety of different reactions. Yeah, so this is also a continuation of that part to remove some reaction steps in the denitrogenation process during hydro denitrogenation. Okay, so now that we have looked at the upgradation and everything, so there is one fraction from the distillation column called residue. So let's say we have our crude oil here, and this is a distillation setup. So in a distillation column, we give in crude oil and we get LPG, naphtha, petrol or gasoline, diesel, and so on. And the final residue in this distillation column comes out through the bottom, and these are usually heavy compounds with a lot of impurities, mainly sulfur, nitrogen, metals, and so on. So treating this residue or upgrading this residue actually improves the cost efficiency of your refinery processes. So what are the ways that by which we can improve this quality or upgrade the quality of the residue is what we'll be looking at in the following slides. Yes, Mr. Hari, you had raised your hand. Why is it? Voice is breaking. Okay. Um, I'll just check my internet. Is it fine now? Uh, Okay, actually, your voice is also breaking for me, so I don't know whether it is my internet issue or can. Oh, okay. Um, okay, am I audible now? Hello. Okay, so it's fine now, right? Okay. Yeah, I think I had some issues with the internet. Okay, okay, okay. Fine. Let's resume. So, petroleum residue and its upgradation. So, in this table, you can see, the different petroleum. One second. I'll just make sure this connection is also secure. Okay. Now it's fine. Yeah. Okay. Right. Fine. So, just we'll resume now. So, if you look at this table here, we can see the properties of crude oil, and then this AR is atmospheric distillation residue, and VR is vacuum residue. So distillation. So as I have shown here, this, let's say we have the crude oil. We first perform the atmospheric distillation, and whatever residue that comes here, we'll send it to another column called vacuum distillation. And usually here, the products that we get are called heavy gas oil and so on. And we get a residue from here also. So this residue is termed as VR in the next slide, and this residue is the AR. So if you look at the properties of VR and AR and compare it with crude oil, we can see the sulfur content and the nitrogen content is slowly increasing, and the amount of asphaltenes or heavy aromatic compounds is also increasing. So, and we can see the API gravity is very drastically decreasing. So basically, you can see how the quality of the oil that is getting changed when we compare the residues with the crude oil. So we want to upgrade these residues so that we can derive some valuable products like gas oil and so on from these residues, and that will add to the cost efficiency and techno economics of the refinery. So the residual oils differ from the average crude oil with respect to its higher viscosity, higher impurities, higher boiling point, low hydrogen to carbon ratio, and high CCR. So CCR is basically contracts and carbon residue. Yeah. So how do we upgrade these residues? So there are different processes. So first one is based on solvent extraction, sometimes called as solvent de-asphalting. And then we have thermal based process, basically cracking process. And then we have hydro processing based or hydrogen based process like hydrocracking. So these two, thermal as well as hydroprocessing, can either be catalytic, or we can use catalyst, or we can do without catalyst also. Right. So let us look into the first process, which is de-asphalting. So de-asphalting is basically, we use a solvent and try to extract the oil, and remove the asphalt content from the oil. So that is basically de-asphalting process. And some of the solvents that we use for de-asphalting are light paraffin hydrocarbons like propane, butane, and pentane, or C3, C4, C5 hydrocarbon solvents. Yeah. So all these different solvents have their own advantages and disadvantages. So for example, propane and isobutane usually gives us higher selectivity to these oil compounds, and they reject all the resins and asphaltates. So basically, if we use these solvents, propane and isobutane, all the light compounds that are present in the oil gets extracted, and all the heavy compounds, including the asphaltenes, gets left back. So basically, this is kind of like a solvent extraction process, this de-asphalting process. And of course, we can use even slightly heavier solvents like butane, pentane, and light naphtha, which is basically C4 to C6. These solvents are slightly less selective than the lighter solvent towards the oil content, and they usually produce higher yields of DAO or DMO. Suitable as conversion for, okay, 1 second. So solvent deasphalting. Okay, fine, fine. Okay. So some of the 1 second. Okay. So some of the general properties of the solvents that we should make a note of is that the solubility of the oil decreases with increase in the temperature for this de-asphalting process. And the selectivity is more at higher temperatures, and they exhibit lower critical solution temperatures. So yeah, that is about de-asphalting process. And then we move into a thermal process, which is visc breaking, or it is an abbreviation for viscosity breaking. Or basically, what we are trying to do is we are trying to break down the viscosity of the residue to its lower values. So visc breaking is a mildly predominantly liquid phase thermal cracking process where high molecular weight hydrocarbons are broken thermally into lower molecular weight ones, yielding products of low viscosity and pore point. So as I said, visc breaking, basically we apply heat to the residue which has a high viscosity initially, and because of this heat that we are supplying, the heavy particles of the residue gets broken down, and their viscosity also reduces, and their pour point also reduces. So that is basically the simple explanation for the visc breaking process. So through visc breaking process, petroleum residue can be converted into small amounts of light hydrocarbons like naphtha, LPG, gasoline, and so on, along with heavy gas oil and residual part, where the with the reduced viscosity. Yeah, and it has been developed to produce fuel oil, resulting in saving the valuable lighter products called cutter crop stocks. It is also used to prepare feedstocks for secondary units like FCC and hydrocracker. So basically, what this means is that the heavy gas oil, HGO, and residues, and all the vacuum gas oil that we produce, we can send it to catalytic cracking units or FCC units, where they are further cracked to produce even lighter compounds like diesel, gasoline, and so on. So that is basically an overview of this visc breaking process or viscosity breaking process. So if you look at the mechanism, this visc breaking process follows a free radical mechanism. So free radical mechanism has three steps. First step is initiation, then we have propagation, and then the third step is the termination. So in initiation, first we take a heavy hydrocarbon, and because we are supplying heat, this heavy hydrocarbon breaks down into two different hydrocarbons with the smaller carbon chain. So here, for example, C6 breaks down into C2 free radical and C4 free radical. So this is the initiation step where a proper hydrocarbon molecule gets broken down into different free radical molecules. Then these free radicals that are formed here, for example, here the C2 free radical reacts with another uh, chain of C6 to form C2H6 molecule and a C6 free radical. So basically, this is the free radical part is being transferred from one hydrocarbon molecule to the other. And the same happens with this C4 also. This C4 free radical reacts with this C6 to produce C4 hydrocarbon and C6 free radical. So these free radicals can then be broken down into smaller chains. So this C4 free radical can then be broken down into C4 alkene, double bonded alkene, and a hydrogen free radical. Or this C4 free radical can form C3 or C2 alkenes along with methane and ethane free radicals. So this way, initially we had a C6 carbon compound. Now it is breaking down to C2, C3, C4, and C5 range compounds. So you can see the carbon chain length is getting decreased, and because of this, the viscosity is also decreasing here, which explains the process visc breaking. So once all these compounds are broken down into smaller products, we need to terminate this free radical mechanism. So to terminate this free radical mechanism, two free radicals will react with each other. So for example, this C2H5 free radical and H free radical will react with each other to form C2 alkane. The same happens with the C2H5 free radical with CH3 methane free radical, or methane free radical with the hydrogen free radical to form other alkanes or gases like methane. So that is about the reaction mechanism of visc breaking process. So typically this is the flow chart for the whisk breaking process. So so initially we have the oil here which gets preheated in a furnace, and then it is sent to a fractionator where it is fractionated or distilled based on their boiling point, and so we get the lighter compounds at the top and the heavier tar compounds at the bottom. And in some cases we can even send this heavy tar from the fractionator to a vacuum fractionator in order to further extract value from this residue from this fractionator. And in some cases we also have a part called soaker drum. So basically whisk breaking is of two types, one with a soaker drum, one without a soaker drum. So let's assume this is without a soaker drum. So in without a soaker drum, what happens is this oil that goes into this furnace. So this furnace will have a lot of tubes. So the reaction or the cracking reaction happens in the tubes of this furnace, and then it is sent directly to the fractionator. But in terms of the soaker drum, what happens is the oil is preheated in the furnace, and then the heated oil is then sent to a soaker drum where the cracking reaction happens. So usually the oil can sit inside the soaker drum for up to 30 minutes, and the temperature is also maintained in this soaker drum for the reaction to proceed. So the reaction of the or the whisk breaking reaction occurs in the soaker drum, and then the broken oil compounds get sent to a fractionator. So these are the two types of whisk breaking that we can generally see. So the first one is the coil whisk breaking, and the second one is the soaker whisk breaking. Right? Yeah. So if we use a soaker whisk breaking process, so to reduce the furnace temperature, a soaker unit is placed between the flash chamber, which is basically the fractionator, and the furnace. And the temperature at the soaker unit is maintained at 440 to 460 degrees Celsius, and 5 to 15 bar pressure is maintained with a residence time of usually 20 to 30 minutes. Right. So all these steps are basically explaining what I just explained in the last slide. So the preheating of the feedstock in the furnace is done up to 335 degrees Celsius, and then the overhead product of the flash chamber or the fractionator gives us the gas LPG, then gasoline, and then gas oil and the heavy tar. So through this process, we can reduce the viscosity of the heavy residue by up to 5 times. And depending upon the reactor design, yeah, so as I mentioned previously, we can either have a soaker whisk breaking or a coil whisk breaking. So soaker whisk breaking is a relatively low temperature process with a relatively high residence time. So the opposite is true for coil whisk breaking. So coil whisk breaking is usually a high temperature process with a low residence time. Then we have another thermal cracking process called as delayed coking. So delayed coking is also a severe thermal cracking process aimed at upgradation of petroleum residue by converting it into liquid and gas products. And along with this liquid and gas products, we also get a solid product called as coke, which is left behind. So the term delayed refers to delayed reaction which initiates in the coil furnace but completes in the coke drum by delaying the process. So do we have, okay, fine. So basically what happens is we have the oil which is sent to a furnace. The reaction starts here, but it doesn't really finish here. So the oil is heated in the furnace and then sent to a coke drum where the reaction happens. So basically, the reaction is slightly delayed from the time at which the oil is heated, and delayed reaction happens in the process, and that is basically why this process is called as delayed coking. So, based for delayed coking, also you have a variety of reaction mechanisms and so on. So, the first one is the primary reactions, which are basically decomposition of smaller molecules. So, for example, if we had a C40 carbon-based compound, it can get cracked into C20 and so on. So, that is the primary reaction. And then the secondary reaction, active products from primary cracking reactions further crack or react to form other compounds. So, for example, we had C40 initially. This gets cracked into C20. So, this is primary reaction. And let's say this C20 further cracks to form C5 and C15. This is a secondary reaction. And for example, this C20 reacts with this C5 and forms a C25. So these kind of secondary reactions are basically the reactions of the products that are formed from the primary reactions. So a typical feedstock in delayed coking is the residue from the vacuum distillation process. Vacuum residue is the typical feedstock, but sometimes atmospheric residue are also used for this process. And typically, the feedstock will contain 6% by weight sulfur, 1000 ppm of metals or metal impurities, and 20 to 30% of contrasted carbon residue. So the major products from delayed coking are gas. Firstly, gas. So we have gas, liquid, as well as solid from delayed coking. So gases are basically in the range of LPG. So usually C3, C4 gases. Sometimes these gases are also called as coker gas. So C3, C4, these kinds of gases, usually recovered as LPG or lighter naphtha, are the gases that forms from delayed coking. And then if you look at the liquid product, it can be naphtha with high olefin content, or it can also be gasoline range products, gasoline, kerosene, and so on. And along with these lighter liquid products, we also have heavy liquid product, gas oil. So something like yeah, so gasoline, diesel, jet fuel. So these are all the liquid products that are found from the delayed coking. And the final product is the solid, which is basically the coke or the carbon residue. So based on their characteristics and appearance, there are three different kinds of coke. First one is the sponge coke, which is shown here. Then we have short coke, and then we have needle coke. And out of these three different cokes, needle coke is the coke of the highest quality. So this needle coke is usually of premium carbon quality and are used in the production of high grade graphite electrodes for industrial applications. And yeah, this table basically represents some of the characteristics of needle coke. But yeah, again, we can see how good this needle coke is compared to the other sponge coke and short coke. Yeah. So delayed coking. This is a brief flowchart. So I think I drew a very vague one in the couple of slides back. So basically, the this is where the feed goes. The feed is heated and then sent to a coke drum where the coking happens, and that is why the process is delayed or delayed coking. And from there, it goes to the fractionator to fraction out the gas, the liquid products, as well as the coke. So yeah, just a brief overview of the flow sheet of delayed coking. So from delayed coking, we can also find the yields of the product, not just coke yields, but the yields of gas as well as liquid products. And there are various correlations by which we can find these yields of the products. So these are the different yields or correlations that we can use to find different yields of the different products. So we have a formula for coke yield, gas yield, gasoline yield. This is basically liquid yield. Liquid in the sense light liquid. We can even use it for naphtha. This formula, and this is gas oil yield, which we usually use it for heavy gas oils. Right? Okay. Fine. I think so. These were the some of the concepts that Professor Mandal has been teaching in the week 4 of his lectures. So now what we'll do is we'll just go through some of the old assignment questions, not the current ones. The current ones are supposed to be solved by you guys. So these are assignment questions from previous years. So we'll just try to solve these questions based on the concepts that we just went through for this session. So the first question: crude oil distillate impurities may be recovered by chemical reagents and the options are as given. By catalyst, by adsorption on place, by caustic sweetening, and all of these. Any guesses for the answer? Yes, all of this is the right answer. And then the second question, C2H5 free radical plus C6H14 gives A plus B. What is A plus B? And there are different options that is also given. So, any guesses what this process could be and what the correct option here is? Option A, okay. Uh, so, as far as I can remember, this is from the vis breaking mechanism. And the right option here is yes, option A, as someone mentioned. So option A, C2H6 and C6H13 free radical is the right answer here. The next question, to reduce the furnace temperature, a soaker unit is placed between a flash chamber and furnace. What is the operating temperature and pressure for the soaker? So I think we just looked the operating conditions just a few slides back. Anyone remember the values? Yes. Option A here is the right answer again. So it is between 460 and 5 to 15 bar. So what are the different names of A, B, C form of coke that we get from delayed coking? Any guesses here? Yes, again it is option A. So this is sponge coke, this is short coke, and this is needle coke. Next question. what is used for the yeah, needle coke, right? So what is used for the production of high grade graphite electrodes for in electric arc steel industry? That is needle, which is the premium quality coke. What is the name of ABC in the given image? So this is a flow sheet of the delayed coking process. So what is A, B, and C? Yes, A is the heater, B is the fractionator, and C is the stripper. So option A here, the heater, fractionator, and gas oil stripper. That is the right answer for this question. So gasoline percent can be calculated by what formula for delayed coking? So which formula can we use to calculate the gasoline weight percent that we get from delayed coking? And the right option here is option C, which is 11.29 plus 0.343 into weight percent of CCR. Fine. So next question. So these two questions are actually slightly related to each other. The first one, vacuum residue have a contraction carbon ratio CCR of 20 weight percent, API gravity of 8.5, and sulfur content of 3 weight percent. It is fed into a delayed coker. It is fed into a delayed coker at a rate of 400,000 pounds per hour. Determine the production of the naphtha percentage. So, you guys want to give it a try and tell me what the right answer could be? Okay. So, this is based on this formula here for gasoline. So, we just saw this formula in the last question as well. So, based on this gasoline, so as I said, this gasoline formula, we can use it for naphtha as well. So, based on this formula, we can find the weight percent of naphtha in the production. So naphtha percent is basically 11.29 in plus 0.343 into weight percentage of CCR, which is 20%. So 20, and that should give us an answer of somewhere around about 18.15. So the right answer here is option A, 18.15. In a similar way, for the same process, so a vacuum residue with a carbon ratio of 20%, API gravity of 8.5, sulfur content 3, it is fed into a delayed coker at the same rate of 400,000 pounds per hour. Determine the production of coke in percentage. So again, we apply the same formula here for coke. Same formula in the sense the formula that is given in the lecture. So coke yield can be given by 1.6 into CCR weight percent. So that means 1.6 into 20, and if we do this, we'll get the answer as 32%. So the right answer here for question number 9 is option C, 32. Okay. Mm. So One more question. Gas oil with an API gravity of 440 and a sulfur content of 1.5 is fed into a hydrotreater. It is required to carry out the HDS or hydrodesulfurization at a severity of 80%. Calculate the hydrogen required in hydrogen per BBL. So for this, I think we have not looked into this in the session today, but it is there in the lecture from Professor Mandal. So if you look at these those lectures, we'll get this formula here. Hydrogen requirement can be calculated by using this formula, which says hydrogen required in H2 per BBL is equal to 110.8 into SF, where SF is the weight percent sulfur in the feed, plus 10.2 into HDS percent, where HDS percent is the hydrodesulfurization severity that is required, minus 659. So if we do apply this formula here, H2 required is equal to 110.8 into SF, the sulfur content is 1.5. So into 1.5 plus 10.2 into HDS percent. So we need a severity of 80%. So that is 80 minus 659. So can someone do this and tell me what you get as the answer? Okay. So if you do this, you will get the answer as 323.2 in hydrogen per BBL. Yes, 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 yes. So the right answer here is option D, 323.2 hydrogen per BBL. Okay. Yeah, so fine. I think we have reached the end of today's session. So today's session was mainly on the upgradation of yes. Yes. Yeah. Uh, hmm, right. Right. The previous lectures, right? The previous last Sundays and the Sunday before that. Um, actually, yeah. Uh, right. Hmm. Right. Yes. 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 I understand. So the thing is actually, I am not like related to NPTEL or their operation. So basically, I am also a research scholar like you. So as a part of my teaching assistant duty, I am just taking these 1 2 hour sessions every week. So all the, I think you would probably have to email the NPTEL team itself directly to see if they can help you with this. But from my side, the only thing I can do is take these sessions and try to clear some doubts. But other than that, I can't do anything with regards to their marking or assignments. I think you can just email it to the general help desk for NPTEL. I think you can get their email from the NPTEL website itself. I don't have it with me now, but if you are not able to find it, just let me know. Next class, I'll try to find it and share it with you. But yeah, you can generally find it in that Swayam portal itself. So you just go to the Swayam portal and click for their contact, and you'll get a help desk email. So you just directly email them with your course details and the issue that you're facing, and I think they'll be able to help you. Yes, yes, yes. So this is the fourth week. So I think 4 more weeks are there for this course. Yes. Mm-hmm. Oh, yes, yes. I think you have to email them and let them know this immediately because yeah. Mhm. Yeah, because I can't really do anything with regards to this because as I said, I'm also a research scholar like you, so I don't have any relation with NPTL. But yes, you try to email them and see what they're saying, and based on that, if I can help with anything, I'll definitely do it. Yeah. Hmm. Um, yes. Yes, yes. So actually, these were provided to me by the NPTL team itself, so that I can make use of these previous year assignments to, teach or use for these sessions basically. So I don't know if it is available for students or anything. This was shared to the not just me, all the teaching assistants who are helping with these NPTL courses. So this was shared with them. I'm not sure if I'm allowed to share these with you, but I'll try to ask the NPTEL team and see if I can share these with you. And if I can share it, then definitely I can just make everything into an email and share it with you. Maybe within a couple of weeks. Yeah. Yes. Yes. Yeah. These were assignments from the last year. So I think every year they have new set of assignments and they just clear out the old assignments. But yes, but I think these assignments most probably won't be shared with anyone because they want people to attend these sessions at least for the previous year assignments. So I'm not sure how whether I'll be able to share it or not, but I'll put up this point and see what they say. Yeah. Okay. If anyone else has any doubts, please ask. If not, I think we can conclude this session. WhatsApp group. No, actually, so the issue with these courses is that some people join today, some people won't attend the next lecture. So for example, the first session I held, we had somewhere around 15 people. Now we are barely having 4 or 5. So the attendance is pretty varied. That's why we usually don't create a WhatsApp group because we don't know who are all the serious learners and who are all not so serious learners. So you can always reach me through the email. I think the my email is also circulated with you guys, but anyways, I'll just put it up in the chat box. So you can always reach me through email if you wanted to ask any specific questions or doubts with regards to this course. But yes, as of now, we have been instructed not to share our personal number as well as create any WhatsApp group or anything. Okay then. Thank you for joining. I'll see you guys next Sunday.